Hi, everybody. So last week we started talking about the refraction or bending of light. And we talked about the circumstances under which this occurs. Light has to enter a new medium so that it changes speeds at an angle. Those are the two things that have to happen: enter a new medium at an angle. And I talked about the analogies with a car having a low tire, and you steer if your right front tire is low, you steer that way. Or if you're pushing that shopping cart at the grocery store and there's a wheel that's not rolling well, the cart's gonna pull in the direction of the wheel that isn't rolling well, right? Similar things happen with light. Light, when it enters a new medium, changes speed, and if it enters that new medium at an angle, it's going to bend. Today, we're going to focus on the changing speed part. We're going to focus on what's happening to the light, or at least by how much a new medium can change the speed of light. And as you might imagine, the more the speed changes, the more it bends. The lower the air pressure in that tire, the more stuck that wheel is on your shopping cart, the worse the pull is going to be. Okay, so we're going to talk about the speed of light and something called the index of refraction today. Now, if you haven't read section 1 of chapter 18, I strongly recommend that you press pause right now and go back and read section 1 of chapter 18. We're going to talk specifically about a table, a chart that is on page 486. And it's a chart of the index of refraction of a variety of substances. Now, I'll tell you, anything that light can go through, any substance that is at least fairly transparent, that allows light to pass through it, has some index of refraction. In other words, light travels slower in that thing than it does in air. And even in air, light travels slower than it does in the vacuum of outer space. So the index of refraction is based on this notion that light travels slower in materials that are not a vacuum. All right, anything that is not a vacuum: air, water, glass, plastic, whatever. Okay. Now, this index of refraction can be calculated if you can measure the speed of light. Now, we can't. We can't measure the speed of light. We don't have the tools for that, but it can be done. Scientists can and have measured the speed of light in a variety of different substances. Okay. And they've discovered this equation, this relationship. N equals C over V. N equals C over V. Now, what does this stuff stand for? Well, again, do the reading, but N stands for the index of refraction. Now, that's going to be a number, and if you look at that chart on page 486, it's going to be a number that is equal to or greater than 1. All right, there are no n's that are less than 1. If you're doing a problem in physics class and you get an answer for n that is smaller than 1, you did not do it right. Go back and try again. All right, n is always at least 1. Okay. C stands for the speed of light in a vacuum. Now, if the letter C sounds familiar to you, where have I heard that before in physics? But maybe not the definition of C. Most people are in that category, right? Where have I heard C before? Well, maybe you've heard of E equals mc squared. All right, Einstein? C is that C, the speed of light in a vacuum. It is a constant value. It's the fastest light can go. Light can't go any faster than it does in a vacuum, like in outer space. And that value is 3.0 times 10 to the 8th meters per second. I'll say that again. 3.0 times 10 to the 8th meters per second. 300 million meters per second. It was really fast. It's really fast. Light travels really fast. The speed of light is sometimes called the speed limit of the universe because nothing can go faster than the speed of light. And in a vacuum, light is its fastest, 3.0 times 10 to the 8th meters per second. Now, this V is the speed of light in a substance like water, glass, air, plastic, as long as it's a plastic you can see through. The speed of light in a substance is the v. Now, this is always smaller than this. No matter what this is, it's always smaller than this. Light always slows down when it goes from a vacuum to something else. Light is always slower in water than it is in a vacuum. It's slower in glass than it is in a vacuum. And that's why V, since V is always smaller than C, that's why N is always at least 1. It's exactly 1. If you look at this chart on page 486, it's exactly 1 if you're talking about the index of refraction of a vacuum of outer space. But for anything else, it's less than 1. Now, if you look at air is only a teensy bit less than 1. It's like 1.00013 or something super small like that. Basically, air is close enough to 1 for us to call it 1, but technically it's not. But everything else is some reasonably larger value than 1. If you look up water on this table, it's like 1.33. Glass, depending on the kind of glass you're talking about, it's 1.5 or 1.6. Plastic, depending on the kind of plastic, it can be a variety of values, 1.3 to 1.8. Diamond is a substance that slows down glass the most of any substance I know about. Diamond has an N of 2.4 something. All right? That's one reason that diamonds are so sparkly. So anyway, the index of refraction of a substance tells us basically how much light slows down in that substance. The slower light goes in the substance, the larger this N is. I mean, think about that. A fraction. This is a fraction, right? The smaller the denominator is, the larger the number is over here. So the slower light goes in a medium, the larger N is, and vice versa. The larger N is, the slower light goes in the medium. And you can use this equation to solve for either N or V. Well, why wouldn't we use it to solve for C? Well, because C is a constant. C is always the same. This is always C. You never have to solve for C. That's C. N and V can change depending on, are you in water or glass or air or plastic or whatever, okay? So this is an important equation. You need to know how to use it. I'm going to give you chances to practice using it over the next few days. But this tells us the relationship between the speed of light in a substance and this number called N, the index of refraction. Oh, one last thing about N. N is dimensionless. What that means is there's no unit, okay? The reason is the speed of light in a vacuum is in meters per second. V, the speed of light in some other substance is also in meters per second. And when you take meters per second divided by meters per second, they cancel out. N doesn't have a unit. It's kind of like pi. Pi is a ratio of distances, the circumference of a circle to the diameter of a circle. Meters divided by meters cancel out. Pi doesn't have a unit. It's 3.1415, blah, 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 blah. N does not have a unit. So when we write an answer for N, we always write N equals 1.33, for instance, for water. And we write N equals, so we don't just have a number floating around, because there's nothing to put after it. You can't put seconds or kilograms or whatever. There's no unit to it. So be sure you write your answer that way when asked. All right, great. That was a great lesson on the speed of light and the index of refraction. Again, go back and read section 1. Watch this video again if you're uncertain. And over the next couple of days, I'll give you some chances to practice using the equation. Thank you.